The second case study, it's all of the above, just like you said. This is a LP system, redesign and retrofit. So on this unit, the existing LP system, it was the entirety of box 6 minus the second stage LP superheater, which you can kind of see in box 4 there. You can see in this process flow diagram to the right there, the black box is around box 6. You can see the majority of the LP section in blue. You can see it's the first stage of the LP superheater right up against the LP evaporator. Then there's a minuscule gap, and the LP economizer is right behind it. You can see that with the inlet headers and the outlet headers at the top. So both the LP evaporator and the LP economizer were experiencing various levels of degradation and disrepair. The tubes had been in service for approximately 17 years, and the leaks were a result of FAC and exterior corrosion. You can see that in these pictures here. The fins are pretty fouled up and discolored. It looks like a combination of ammonia salts and maybe some insulation. It's hard to tell. There's some pretty nasty corrosion on the tube bend, seen there on the bottom left. Kind of looks like some kind of growth or something. And then, of course, we have very, very classic two-phase FAC in the picture in the top left. You can see the characteristic black and shiny kind of horseshoe crab pits, the wear pattern on the ID of that tube sample. I believe that tube sample is from the upper end of the Harp near the upper header. Of course, all these tubes were carbon steel, 17 years old. So this plant was built around 2004. Most everyone still using carbon steel in the back end. It's still used unless it's spec'd out to be low alloy. I guess that's a point for anyone who may be involved in bidding a new combined cycle unit. You have to write that into the spec. The capital HRSG business is brutal. That's why you see carbon steel everywhere. You got to write it in if you want it, spec 11 or 22. Kind of like Barry was saying, as well understood as FAC or as good a program as you have, there's going to be upsets or transients. It's cheap insurance to just put low chrome in there to begin with. The cost difference between carbon steel and T11 or T22, it's very small in the grand scheme of things. There's very little cost difference, but you have to specify it up front. And I'm telling you that as I used to be on the capital side selling new HRSG units. I was an account manager for about 3 years, and sometimes if you price in the right solution and it's not specified, you'll lose the job. So it's very competitive. You just got to write it into the spec. But that's why you guys are going to see carbon steel out there. People only put chrome in there if they're forced to. But anyway, the LP evaporator was carbon steel construction, and FAC was the primary damage mechanism. We can see that very clearly from the picture on the last slide. The LP economizer was carbon steel as well, but it was serpentine in design. So FAC and external corrosion weakened the tubes, but the inherently flawed support system ultimately led to the mechanical failure. I'm sure many of you are familiar with this design and how it works. This LP economizer, it's a serpentine bundle. That means all the flow enters the inlet header on the cold end and follows a serpentine flow path through the exhaust gas path in a pure counterflow arrangement across all 3 widths of the boiler, and then it combines into that outlet header. So there's no intermediate headers at the top. They use these return bends that loop over these pipe supports, and those are in turn supported by the main headers. There are headers at the bottom, and these bottom headers, they do allow you to drain the circuit, but where you really need them is at the top, both for a more robust support method, but also so you can vent the circuit and tie the whole thing together to thermally expand in a uniform fashion. Because that's what happens here. With each of those return bend loops, it's free to grow thermally at a different rate than its neighbor. So say you have a not quite uniform flow through the whole circuit, or higher heat flux through the edgemost tubes, which does happen. The tubes are going to operate at a different temperature and they're going to expand differently. Well, that support bar is fixed. So you have one tube that's hotter than another, which means it's going to be longer. And in many cases, it's going to disengage from that top support bar. So what does that do? It causes the tube next to it to bear more weight or support than it's designed to. So pretty soon the whole bundle is only being held up by half the tubes. So now you have return bends that are under higher load than design, but also potentially wearing across the support bar as it engages and disengages on a cyclic basis. So you have external corrosion, you have some FAC, and that weakens the system, but it's no wonder that there's failures. On top of that, this is a bundled design. So the construction of this, everything is tied together. The LP superheater and the LP evaporator, they're tied together at the tube sheets. All the LP economizer rows are tied together at the tube sheets, and they're connected by the return beds. So replacing, or I'm sorry, separating or replacing any single tube, very, very difficult. And I mean, this is pretty evident from the picture, right? Those return bends, they form like the wall of a jail cell. There's no way to separate anything. And even if you could separate them there at the upper header location, they're tied together at the tube sheets. They're encompassed by a continuously welded tube sheet, every 10 feet or so. And, good luck separating those. So, in the tube spacing, it didn't really allow for good access or cleaning. You can see that by the picture. I mean, it looks like there's maybe 1/8 of an inch between those fins. They're just jammed way up against each other. They just weren't designed to be serviced. So the best solution for us was to redesign the whole system using T11, P11. You got to get the low chrome in there. It's largely going to knock the FAC right out. But the new design is fully ventable and drainable. So the way we like to do this is to have a top header and a bottom header on every Harp, and not to build it as a bundle. Instead of a return bend, we use piping crossover that's not bearing the weight of the module. And this interconnecting piping, it needs to be low chrome as well, by the way, don't forget that. And then there's a vent and drain at every high point and low point of every circuit in the design. So there's no chance of vapor lock. And oh, by the way, you can now drain your system faster too, because you open up the vents and now you're not trying to pull a vacuum. You can see this new vent piping. It's running out the top casing in this diagram on this slide. We used to tie this into the drum, but honestly, we're talking about such a small amount of steam that it's not worth saving, especially if you don't already have a drum connection to tie into, or a good method to introduce the steam into the drum. It's just more trouble than it's worth. What's usually done today is you just route it to a safe location up at the drum elevation. The drain piping just ties into the blowdown tank as it did before. So this new design, it has independent support and thermal growth for each module. Since we've separated this new heating surface into discrete modules with top and bottom headers, we can now hang the top headers from a traditional hanger rod system. So each header has its own hanger, and every model can grow and move independently. We don't tie our tube sheets together either, because adjacent modules may grow differently. We don't want to put undue stress on the connection there. It needs to be a bearing connection only, restrained so that it can't move out of plane, but free to slip between each other. The new design, it has a staggered tube pitch. It's actually large enough to allow for an ice blasting lance to pass through all the tube banks. So on that point, when it comes to cleaning, here at Vogt, we don't necessarily endorse any one method. I'm pretty familiar with most of the options out there. There's obviously ice blasting using a spreader bar, as with PIC, or without. There's the GE Bang and Clean or pressure wave technology, I think it's as they've rebranded. There's acoustic cleaning. There's a combination of the two with Epic, where they use a combustion pressure wave focused with an acoustic horn. So all of these have their own unique access profiles and cleaning durations. But the point is now there's enough room to scaffold if you need to. And that was really a big deal to this plant. They actually wrote it into their spec that it needed to be 26 inches. And we made that work. So not just for cleaning, but access to the whole box has been improved for whatever reason, maintenance, cleaning, or whatever. And finally, the new design, it has equal performance as the OEM design. So no re-rating is required. Now, some astute individuals out there might ask, all right, well, in a situation like this, why don't we take the opportunity to increase the performance if we're redesigning the thing? And that's a great thought. But the problem we run into is that any increase in steam production, it almost always follows a sliding pressure curve and increases the pressure. And the problem there is your existing piping, your existing drum, all your weld details, and especially your safety valves. They can't take that pressure increase. So you would have to replace all those pressure parts. I know it seems crazy that a mild pressure increase can't be managed with the existing equipment, but you'd be surprised how even a small fillet weld is sized to MAWP and it doesn't have much margin in it. Fortunately, I've looked into this before. So we want equal performance, not better, not worse. And maybe equal isn't the right word because this heating surface is obviously pretty fouled and degraded. What we actually want is a return to baseline or design performance, like when the unit was clean and new. And we can do that. As an OEM, we have our own thermal rating software, like we talked about earlier, and so we can hit this dead on. So again, since VPI and TEiC had been awarded this job on a turnkey basis, we could coordinate internally the best demolition, design, fabrication, and installation methodology for maximum constructability. Through rigorous planning, this full box 6 retrofit was accomplished in a 30-day breaker-to-breaker outage. And, this kind of goes to the point that I tried to make at the very beginning about planning the whole project together for a successful outage. As a designer, I could have said, oh, I'm going to deliver a new bundle to be dropped in through the top, because that's how the original construction of this unit went together. But you'll notice the drum was not lifted. And this is a big deal. Anyone who's ever considered disconnecting all the piping and instrumentation around a drum will agree. You don't take that lightly, and it's not cheap. So we came up with this construction plan together with all our sister companies involved. And we had a vested interest in each of us being successful. We wanted a successful project, not just success for our individual pieces. Not on the design side, the supply side, the construction side, but all together. So this does require some pretty critical coordination on some design aspects like the lifting leg orientation. Whenever we all get together to bid one of these, one of the first things we discuss is the high-level strategy. We ask TEiC, Tim, hey, how are we coming in the top, the side, or the back? How are we moving the harps in direction of gas flow? How are we moving them transverse to gas flow? How many lugs do we need? And what orientation do they need to be in? Because remember, you don't want a side load lug that isn't designed for it. And then BTA, our Harp shop in Lyman, South Carolina, they plan for that up front. There's no surprises when the Harps arrive at site and someone says, oh crap, there's not enough lugs, or they're in the wrong orientation. We're all working together towards that same end. So you can kind of see that in those pictures down there. I think each of those Harps have 4 lugs on them each. So often, the header is just completely taken up by lugs. So then, the NDE and hydro test plan between the shop and the field can also be planned and consistent. I think that picture at the top is the post-weld heat treat in the oven for the tube to header welds, but that lower right picture is showing the shop hydro test of the whole Harp assembly. We always do this to make sure we uncover any weld issues in the shop before anything makes it to the field. But what we also do is we make this an AI witnessed shop hydro test. Then when we go to the field, we can often perform 100% NDE on the field welds and forego an in-service hydro. But this only works if you plan for it. You need to plan up front. You need everybody working together to coordinate this. If you're holding a material-only contract, you might say, I'm not doing a shop hydro because it costs me extra. But I guarantee you it's nothing compared to an in-service hydro. And then finally, the delivery order of the Harps could be optimized to reduce double handling. This might not be super obvious at first, but which Harps do you think you want delivered to site first? I know not everybody can answer. Is it the first one going in? No, it's not. It's actually the last one going in. The reason for this is because no one is delivering just in time. Some of you might know my colleague, Tom Price. He used to make this a joke. He would say, just in time is a great concept, but he would always say, he's going to have truckers be his pallbearers at his funeral so they can let him down one last time. And the joke obviously being that, the truckers, they never come through. Just in time, underhook, it never works. And planning your outage to go that way is not planning for success. What you want to do is you want to deliver the Harps to a site in a pile, ready to be lifted and installed. So your main crane that you're paying an arm and a leg for isn't just waiting for some truck driver to deliver just in time. He makes less than that crane guy. It's not worth it. So you want your last Harp to be delivered first, so it's at the bottom of the pile. And it's this kind of planning that makes for a successful outage. So we kind of talked about it already, but instead of a bundle that would require a large crane and a big access window and also lifting the drum, we used the discrete header design that allowed Harps to be loaded individually. So you can see these Harps being slid down in that picture at the top. And you can see all the new feeder and drain piping in the basement shot here at the bottom of the page. Catalyst changeout was accomplished with the same crew in the same outage. 30 days breaker to breaker. You just got to plan it right. So I'm going to turn it over to Tim again to speak a little bit more to the construction side of this job. Tim, you there?
Yeah, I got it now. Thank you very much, Greg. If you'd go back to those first pictures, Greg, and I'll start from there. Sure. So just to let everybody know, this is one of our biggest challenges. This is what we see the most within our group is FAC issues. We are asked to change out Harps probably primarily more than anything else. And that has driven this gas side of our business. We have developed 4 to 5 exclusive HRSG construction teams that exclusively do HRSG type work, Harp replacements, burner installs, any component to do with the HRSG. They're a specialized group that we've developed throughout the country. They're regional so that they are accessible to different areas of the country. This specific project created quite a few challenges. So first of all, we had to determine what we were going to do in order to get these modules demoed from the unit. They were tied together. There was a triple wide. There's not much room. There's not really any space. These modules weighed around 150,000 pounds, which is very large. Coming out of the top of the unit would have created a major. You would have had a major crane with a large radius and a large boom length. So we had to find a kind of a way around that. And as Greg mentioned earlier, we did not want to remove the drum. So we actually determined that a top approach was the best response for this. And in order to take them out, we could not take them out in one complete piece. So we worked with Vogt to develop a proprietary engineering and lifting plan that we utilize throughout the country, which allows us to separate these modules and remove them in pieces that are manageable by a smaller crane, as well as a smaller entry through the top of the unit. That allowed us to remove them in multiple pieces and still support the harps from the existing structure up top. Next slide. So as you can see, the serpentines, they do have some pipe that go through those, and we utilize some of that pipe as well as that structure up top to support as well as separate these modules. We then attached our crane and our rigging and removed those individually through that access opening in the roof. And of course, the first bundle that we removed was very difficult. It was very tight. There was no room to work around, so we were definitely in tight quarters. But it is achievable. Next slide. And once they were removed, we've got a photo of a crane laying one of the old pieces down, and we'll go to that next. But once they were removed, as Greg spoke to, they engineered a individual harp design, which of course fit through our opening that we, the access that we made through the top of the unit. We were able to lower those harps through that access, and then we were able to relocate them to their final resting place and then permanently affix them to the unit. Of course, after all the harps are in place, then your riser pipes, your drains, everything else is reconnected, as well as your opening up top. Next slide. This is the slide I referred to. So you can see one of these harps. It's actually not a harp. It's one of the components of the module, the bundle that we brought out. So of course the header comes out intact with the tubes affixed, and then we brought out this entire bundle in about 5 or 6 lifts, and we just lower them to the ground. We later demo and put into scrap containers for removal off site. Next slide. And Greg spoke to earlier the lifting lug configuration. It's very important to be able to determine the orientation of these lugs prior to the harps being built. And the installation methodology is key in deciding what side load or what kind of pull you're going to be placing on these lugs. For anybody that will be doing one of these projects in the future, that is a very crucial piece of information you'll need to determine. Next slide. All right. So before I get into the final tie up, one thing we did not mention is that in order to upright these harps, you will need, or there will need to be a uprighting frame. That frame will be engineered, or on our projects, Vogt engineers and provides us that frame so that when the harps arrive on trucks, there is a frame provided. Also, there is a unloading frame that we use to unload the trucks and stack the harps. And then when it's time to put the harps in the unit, we utilize that unloading frame to place the harp into the uprighting frame. That uprighting frame is then used to support the harp so that there is no deflection of the harp when you raise it into the vertical position. Once it's in the vertical position, you can then remove the uprighting frame. You can take your primary crane and take the harp away from the frame and lower it into the unit. A very key component that has to be accounted for and definitely has to be engineered and sized appropriately in order to maintain those harps and prevent any damage from happening in the uprighting process. And then lastly, after the harps are in and they're permanently affixed to the unit, then we do our final drain weld, header welds, and then repair any casing, any liner, anything else that we had to disturb in order to make these replacements. And that's pretty much it from my end, from a construction end. I'll turn it back over to Greg.
Yeah, thanks, Tim. That frame, you're talking about basically not having the harp do this big bend here, right? I guess
Yeah, yes. So that deflection is, of course, what would happen to your new harp if you tried to upright it without a frame. Now, those are the old demoed harps, so no reason to keep those from deflecting. But if you did that to your new ones, you would damage a lot of a new material. So yeah,
it's like a wet noodle.
exactly.
A
And
lot of people are
these things
surprised.
these things can be up to 80 foot long, and they can weigh 40 to 60,000 pounds a piece, even heavier. So that kind of weight and that kind of length causes for quite a bit of deflection.
Right. Thanks, Tim. Okay, so that was it for this presentation. So I'll turn it over to Barry for the Q&A and discussion.
Yes, again, Greg and Tim, thanks very much for a very nice presentation there on some of the aspects of replacement for this terrible mechanism that we've all been dealing with for more than 20 years. Now, are there any verbal questions? Just raise your hand and Scott will unmute you. Are there any questions, Scott?
Yes, Barry. I would like to ask a question.
Yes, go ahead.
Thank you. With the new design of the LP panel or the LP module, and with the new material, now what is the timeline now for having a tube sample to see if there's an FAC development again, or to verify that it is a successful design and good for reliability of the unit? Thank you.
Yeah. Barry, I might ask you, I mean, in our experience, low chrome really knocks this stuff out, but I'd be interested in your take on that.
Yeah, Gilbert, it's quite clear, like Greg says, you only need, from a scientific point of view, just a little bit of chromium. You know, there's really no agreement on what it is, but if you have more than 0.1% chromium, then you'll essentially prevent FAC, both single phase and two phase. and Greg has indicated here that they used TMP 11. So that is 1¼ chrome. So it would be extremely unusual for any FAC to take place with that material.
Thank you very much.
Yeah.
Thank you.
So, is there anybody else with a question for them?
Hi,
So,
Barry. We do have a question in the chat.
yeah, yes, I'm just going to, Scott, I was just going to do that. I just want to see if there's anybody else. So there's a question, a written question here from Gray S. And as he's written it, I'll read it out. If he wants to come and amplify it a little bit, it's okay. So the question is, was the LP system replacement planned well in advance, or was done in an emergent situation after failure? Interested to know the inspection findings during the statutory inspections done in the 17 years to foresee the upcoming failure.
Yeah, that's an excellent question. I'll answer it in two parts. The first is with a Harp retrofit of really any sort of size, even if we're only talking really one Harp. It is very rare that anybody is going to have enough stock tubing to build that Harp. Now, we do have Diego on the line. He runs our BTA shop, and they do stock tubing for emergency outages. But I don't believe that we ever stock sufficient quantity for a full project. So what that means is that we're at the mercy of the tube mills when we execute something like this. And, you know, depending on the flavor of the month and the market conditions, just to get a tube X mil, you know, you could be looking at somewhere between 12 to 18 weeks just off the cuff. So generally, I'd say people are planning these. A good planning, successful outage is probably in the 35 to 40 week time frame. That gives everybody enough time to procure the materials, to build the Harps, to lead to a successful outage. We've certainly done them quicker than that, but the idea of something failing and then being able to replace it within a standard time frame of like 30 days, that's just not going to happen. You're going to have to repair it in that time frame, and then you're going to have to plan for a more major outage down the road. Does that answer your question? Oh, and I'm sorry, you had another point about the inspection.
Yeah.
I was going to say, so the way this project came about is they did do regular inspections, and what they found, you know, it kind of starts with onesie twosies. You know, you get a couple tube leaks, you deal with them, but then eventually they get bad enough that you can't even stay up and running, and so then you have to plan for your major Harp retrofit. That's usually how it goes, and this plant was very similar. They'd seen tube leaks for a long time. It was just that it finally got bad enough that they said we have to do something about this.
Yes. Yeah, Greg, can I add a little bit? Is that okay? It's your show, but we have a lot of experience with this. So unless Bob and I have done an assessment of the plant for FAC and cyclochemistry, or in the case that you indicated, where there's been a failure or multiple failures, it's extremely rare for plants to conduct just an FAC inspection like Gree is asking here, just for the sake of doing it. It almost never takes place, and in all the cases, you know, Bob and I have probably done close to 300 plant assessments worldwide, and I've been involved in so many FAC failures. The failure is usually the first thing that happens.
Yeah.
So the much better way of doing it is, and I was going to mention, is that your photos clearly illustrate like we see in many of these failure situations, that the chemistry, the cycle chemistry on the unit is extremely poor on the unit, and that's the way out of the situation, you know, to conduct the assessment and to upgrade the chemistry. Are there any more questions, Scott? Any written?
Yes.
This is Scott Wambeck. You know, in line with what you're saying, Barry, of assessing units, prevention, of course, is always the best way. So we've got some units that are slowly wearing, but they're not ready for retrofit. What's your experience been with film forming products in terms of helping to manage two-phase FAC where you're struggling to do it in another way?
Are you asking Greg or me?
Oh, you. I think. I mean,
Please, Barry, go ahead.
Is Greg, is that okay with you?
Yeah, absolutely.
We specialize, of course, in film forming substances. I've run 4 international conferences on them, and to answer Scott's question, just very quickly, if you want any more, just contact me, Scott. But you know, like it's there's no absolutely direct evidence of reduction of the failure mechanism, but there is direct evidence of a reduction in ion transport. And what we're trying to do now is bring those two situations together. In that if there is a reduction in ion transported in the low pressure part to the high pressure part of an HRSG, then we would like to be able to directly relate that to the situation in the tube that Scott that Greg showed, classic two-phase FAC that you can identify from inspection, and you could actually make a correlation if anybody decided to do that. In terms of single-phase FAC, there's quite a lot of evidence that the film-forming substances can address single-phase, and we know that from the color, from the internal color of the tubes in the location where it happens. It doesn't happen in the same locations that Greg has indicated here. On these types of units, it would happen at the bottom where there's water and not two-phase mixture like at the top. Scott, if you need anything else, just contact me, and I can get you in touch with some of the information.
Great, thank you. That was really good. Hey, Greg, I do have a question for you also. You discussed early on that you redesigned the tube harps a bit, you know, because you changed the material, there's a slightly different heat transfer coefficient, and you went to staggered pitch to get some cleaning lanes. How about for finning? You know, back, quote unquote, back in the day, you know, when we were kind of limited to 6 fins per inch on a tube, that's at least somewhat cleanable. Now, of course, newer technology, we can do 7.5, maybe even 8 fins per inch. I've been avoiding that in my retrofits because I'm worried I can't clean it, or I'll be less able to clean it. Do you guys have a recommended maximum for fouling and cleaning?
Yeah, that's a good question. I haven't specifically run into any instance yet where we've had issues. I mean, like you said, certainly on contemporary units, everybody's finning up to 7.5 or 8 fins per inch. So maybe we just haven't seen it yet because a lot of those units haven't needed to be cleaned. But all these new units, they do have that higher fin density. What we can also do is, you know, the fin thickness has gone down over the years. Right, it used to be real standard 1.2 millimeters, then we went to 1 millimeter. Now a lot of the times we're 0.8 millimeters. So that also helps you put in a higher fin density. That was definitely one of the tools we used in this redesign. I don't think we had to go that high, but we certainly increased our fin density on a lot of the modules. We also got a different efficiency by just using a different geometry. You know, older units, they used a much larger tube with a much higher fin. And from a heat transfer perspective, we found that's not quite as efficient as a smaller diameter tube with a shorter fin. So we can actually get, you know, equal performance often in less space just by using a more optimal geometry. So that was another one of the tools we used here. So just like you suspected, we did kind of play with that in the redesign.
Good.
Great, thank you.
Yeah, Scott, thank you very much. There's one more written question here from Marcus Woodgate, and he says, what is the relationship of FAC with the water treatment, volatile and phosphate? Greg, do you want to answer that, or you want me to do it?
I'd love for you to take that, Barry. You're an expert.
So, yeah, so a simple way of answering it is that we get asked these types of questions quite often, and Bob and I have put the very latest information on the HF website. Bob can tell you exactly where it is, but the latest review on FAC I just wrote 2 years ago, and that includes that information. But we have a basic set of rules for HRSGs and FAC. There's 4 of them, and I'll just very quickly indicate them to you. The first one is always operate with an oxidizing treatment. So that means do not use a reducing agent or an oxygen scavenger in these combined cycle plants that have HRSGs. The second one is that you need to adjust the pH, so you minimize the amount of total iron that's transported. And I suspect in this case the pH was quite low, probably 9.1, 9.2 or something like that. And so the third rule is adopt a total iron monitoring program so that you can determine what is the optimum chemistry. And the fourth is not a direct one, but it's related to the amount of deposits in the HP evaporator. You want to keep those below a certain level. And there's guidance documents freely available internationally that people can get. So there is a direct relationship. FAC is directly controlled by the chemistry, obviously, and so if you use the oxidizing treatment, then you generally eliminate any possibility of having single phase FAC. And in the case that Greg has mentioned here, in terms of 2-phase FAC, you've got to increase the pH. And sometimes if you can't increase it with just ammonia or an amine, you have to add a solid alkali, such as phosphate, or in some cases around the world they add caustic. So, but you can get all that information in the latest review, and Bob can hopefully tell us where you can get that. I think it's on the HF website.
Yeah, I can tell you after Scott tells me.
Oh, okay.
So Scott, do we have that stuff on the website yet?
Not yet, but it'll be there within the week.
Okay. In the meanwhile, you can find that information on the competitivepower.us website for download.
Or Bob, they can just contact me and I'll send them
Yep.
a copy. Are there any other questions on this most important topic? I don't see anything else written, Scott.
Nope, and we're right on time. So
I just have one more question, if I'm allowed. I had a question, not a comment. So, Greg, I'd just like to confirm that when you replace these low pressure systems, that you replace the risers and the belly plates in the drums at the same time?
It can depend on the project. That's largely to our customer. I mean, we know that area is susceptible. We do whole separate projects where we just replace the belly plates, right, with low chrome, because obviously, I mean, that's almost a wear part. If it's carbon steel, it's going to wear out very quickly. I don't believe on this project we went all the way to the belly plates. I believe we connected the piping about halfway between the modules and the drum. Tim might be able to correct me if I'm wrong. You know, when we cut into that, if we find bad material, you know, we'll go back to the customer and say, hey, we really need to change this. But unless we found that, and if they didn't spec it, you know, sometimes that scope is excluded.
Yeah, so that's always cost driven. So we do definitely bring that up to the customers anytime we find that. And yes, we have changed all three of the components you mentioned at some facilities, and then some facilities elect not to do that. But we do always let the customer know the situation and what needs to happen. And then it's ultimately up to them to make the cost decision.
Yeah.
Yeah.
So you can tell. So one of the first things that you would look at for units that have as bad a chemistry as indicated in this case, you would want the risers to be straight and not have any bends in them. If they have any bends in them, they would be susceptible. And then you might want to do some inspection on the extradose of those bends, because that would be a prime location with two-phase FAC as bad as you showed.